Welcome to this explainer for the Grade 7 Mathematics Supplemental Lesson Probability Mini Project. I am so excited to guide you through this today. We're going to do something mathematicians absolutely love. We're taking abstract concepts, luck, chance, randomness, and translating them into concrete reality using numbers. By the end of this, you'll have a totally new lens for looking at the data and claims you run into every single day.
Okay, let's dive into this. Here's our roadmap for today. First, the language of chance. Next, modeling the odds. Then, theory versus reality, and we'll wrap it all up with check your understanding.
All right, Section 1, the language of chance. Before we calculate anything, we really need to nail down the vocabulary and rules.
So, before we crunch any numbers, we have to understand the basic ground rules. All probability fundamentally describes how likely an event is to happen, right? And it operates on a strict mathematical scale ranging from 0 to 1. A probability of 0, that means an event is completely literally impossible. On the flip side, a probability of 1 means it's absolutely guaranteed to happen, no doubt about it. And everything else, every chance, every risk, every likelihood lives somewhere in the fractions and decimals right between those two numbers.
Now, a massive part of statistics involves using data to make claims about a larger group, which we call a population. But, and this is a big but, the quality of that claim relies heavily on having a true random sample. This means every single individual in the population has an equal chance of being chosen, completely without bias. If your sample isn't random, well, any claim you make about the whole population simply won't be valid. It's kind of like judging a whole pizza just by tasting the crust.
That brings us to how we actually calculate chance on paper. Theoretical probability is our mathematical expectation. Basically, it's the perfectly calculated likelihood of an event occurring, assuming everything operates flawlessly before we ever even run a real-world test. It's what should happen in a perfect world. And, it acts as the necessary counterpart to our next crucial vocabulary word.
Experimental probability, which is exactly what it sounds like. It's the actual messy, real-world result that we observe after physically conducting an experiment, running a simulation, or doing a set of trials. Now, whether you're dealing with theory or real-world experiments, things can get pretty complicated quickly when multiple outcomes happen at once. We call those compound events. To make sure we don't miss any possibilities, mathematicians use structured tools like lists, tables, or tree diagrams. These are absolute lifesavers for keeping our calculations perfectly organized and accurate.
Moving right along to Section 2, Modeling the Odds. Let's look at a practical, step-by-step example.
I want you to imagine a bag containing exactly 10 tiles. Check out the breakdown. 3 of the tiles in our bag are red, and the remaining 7 are blue. This is going to be our perfectly controlled little environment to test out some simple probability. So, if we reach into that bag without looking, what is the theoretical probability of pulling a red tile? Well, there are 3 red tiles out of 10 total tiles, which gives us the fraction 3/10. That easily converts to the decimal 0.3, giving us a 30% chance. We have a 30% theoretical probability of pulling a red tile. Boom! Simple, straightforward, and super logical.
Okay, Section 3, Theory versus Reality. This is all about expectation versus outcome.
Now, what's really interesting about this is it brings us to the absolute biggest misconception in statistics, the clash between theoretical math and physical experiments. Notice the distinct difference between the short run and the long run. A probability model absolutely does not guarantee what happens in the short run. If you pull 10 tiles, you might not get exactly 3 red ones. The exact numbers will vary completely unpredictably. However, probability predicts long-run patterns. The more trials you run, the more those unpredictable short-run results will predictably align with your theoretical model.
Let's apply that directly to our red tile example. Say we pull a tile from the bag 100 times, putting the tile back after each draw, of course. We expect to see red about 30 times, based on our 30% model. But reality means the exact short-run result will still vary. You might pull 28 reds or maybe 32. The math gives us the expected long-run pattern, definitely not a short-run guarantee.
All right, let's wrap this up with Section 4, Check Your Understanding. Let's tackle some practice questions.
Time to apply what we've learned. Think back to the concepts of population and random sampling we just discussed. Here's your first question. Why is surveying only your closest friends likely biased? I'll give you a second to think about it. Got it? The answer is that the sample probably won't represent the whole population. Your closest friends usually share similar interests, backgrounds, or ages with you, right? So, because they don't represent a true, unbiased random sample, any inference you make from surveying just them wouldn't be valid for a larger, more diverse group.
Okay, question 2. Let's look at calculating odds. If a spinner has 8 equal sections and 2 of them are green, what is the probability of the spinner landing on green?
Let's break down the math step by step. You have 2 green outcomes out of 8 possible outcomes, giving you that initial fraction of 2/8. We can simplify that down to 1/4. And converting 1/4 into a percentage gives us our final answer, a 25% theoretical probability of landing on green.
Finally, question 3. Let's test your grasp on long-run patterns. If an event has a theoretical probability of 0.75, how many times would you expect it to occur in 100 trials?
The correct answer is about 75 times. Notice how absolutely crucial that word about is. We convert the 0.75 to 75%. 75% of 100 trials gives us our mathematical expectation. But remember our huge misconception correction from earlier. It's an expected long-run pattern, not a strict guarantee for the exact outcome.
You know, you've done an incredible job navigating the mathematical language of chance today. But before we go, I want to leave you with a thought that extends way beyond the classroom. How do random sampling and bias affect the news, the advertisements, or the data claims you see on your social media feed every single day? Now that you understand how these numbers actually work, you literally have the power to question the data around you. Keep analyzing, keep asking questions, and I'll catch you in the next explainer.